Okay, are we on? Is this on in the back? Can you hear me? Yes? Good. Okay. So, last time I bug you about this, registration ends tomorrow. If you're at all interested, please go ahead and register. There we go. All right, some administrative details. We're almost done grading. I thought we'd be done by today. We're not quite done. One of the TAs is a little bit slower than the others, or actually had a harder one to grade. But we're almost done. We'll probably be done by later tonight. I'll defer going over solutions until Wednesday. To be frank with you, I don't really know how we return exams that were graded in Gradescape. I think you can go to Gradescape and see your grades, I believe. First time I use it, so I'll figure it out tonight. Question day 6 is due today. Lab 4 is tomorrow. Question day 7 and question day 8 will come out Wednesday and Friday, respectively. Now, about the labs. The labs are made available to you 5 minutes before your lab section, and they close at the end of class. There's a 5-minute grace period you should not rely on. Every lab, and it's getting worse, I get a bunch of emails saying, oh, we almost finished and I didn't submit. Can you grade my lab? I'm not doing that. You need to get it uploaded to Icon. Upload it multiple times. You get a problem done, upload it. You get the second problem done, upload it again. We only grade the last submitted copy. Now, this may sound like I'm being a jerk, but the fact is, I literally get 500 to 600 emails a day someday. I cannot be dealing with individual labs, individual questions of the day, and stuff like that. That's why we use Piazza. Your job is to get your assignment done by the end of class and upload it, and everything will go smoothly, okay? So please don't take advantage and say, well, I was only a few minutes late. If you missed the deadline, you missed the deadline. That's how we have to be for the rest of the class period. Don't forget the conference. If you register, which closes tomorrow, you're eligible for the door prizes and stuff like that. There's also a social hour. There's free pizza on Friday night and free something else on Saturday night. Game nights, video game nights, board games, and stuff like that. So the speakers are really good. John Laird's at the University of Michigan. He works in autonomous systems and machine learning. He's long been associated with this large project on building a cognitive architecture, which means building a machine that thinks not just it does AI stuff, but does it the way humans would do it. Chris Hammond's at Northwestern. He also has a startup on the side. He's a natural language processing person, and he's really entertaining. His TED Talk's really good. Both of these guys are old friends and really well regarded in the community, so this is something that would be worth seeing. Kelsey Hubner was you 10 years ago. She's a graduate of our program in the informatics program. She's an AI manager at Microsoft now, started in HCI. She's going to tell her story about how she graduated from Iowa and what she did on the job market and sort of her journey over the last 10 years. If you're wanting to see into your future, this might be a good talk to attend. Casey DeRue is an Iowa professor in physics, and he's using machine learning basically to detect strange anomalies in astronomical images. And so this is a really applied talk, but it's nice to see computing applied to something else. So these are 4 talks that will be held. The first 2 are on Friday, the second 2 are on Saturday. Okay, so I'm really pleased with how we're using Piazza. There are a lot of great questions that are being asked. Some of you are even stepping in to help answer questions, which I think is just ideal. You learn as much by trying to answer as you do by asking, so this is great. Here are some appropriate questions for Piazza. Can I use a for loop on question of the day 17? I'll tell you yes or no. Can you post some sample problems so I can practice? Absolutely. In some lecture you said, and I didn't understand. That's the best kind of question to get. Why does this piece of code generate an error? You can insert your code here. Note that only that last question, the one where you post your code, needs to be private. Everything else can be public. If you have the question everybody else does, you won't show up. You can post anonymously, and that way I don't have to answer the question 3 times. And the only reason this last one should be private is if the code that you're posting pertains to a still active question of the day, a lab, or a homework assignment. Otherwise, just go ahead and post it. And here's an example that is not appropriate use. I get a lot of private questions. Will I get full credit for this answer? So I'm not going to answer those. I'm not going to answer them on Piazza. I'm not going to answer them in my email. I use an autograder because you guys generate 1,200 functions a week on a slow week. That's a lot of grading. The only reason I use an autograder is I can't do it by hand. So if you ask me, will this get full credit? First of all, it's not about the credit, it's about the solution, right? You're here to learn. 1 point on the question of the day, when we're tossing 30% of them, and altogether they're only worth 5% of your grade, is not something I want to agonize over. It's not significant. What is significant is that you understand the concept that I'm trying to teach. Which brings me to the next part of this, question of day 6. This is a specification for question of day 6. Now, I did say, I think, in class not to use a comprehension. Actually, I think I put it in the spec because we hadn't really covered comprehensions yet. Although this is a fine question where you could use a comprehension if you wanted to. And in fact, I said, we're after a solution that relies on splitting the string on spaces and adding the links of the resulting words together. Your solution should not use iteration for a while. We didn't mention comprehensions because we hadn't covered them when the question was released. But you may use the iterative constructs discussed in this lecture. Now, this is a pretty strong hint. And I was surprised at the number of solutions I got that didn't take the hint, like they didn't read the specification. So for example, here's one I got. Somebody sent me this and say, well, I get full credit with this. Well, that solution really does work. But it's really, really ugly. I mean, we're in week 5 now. You shouldn't be doing x equals something, y equals something, z equals something. I mean, forget that stuff, right? You know how to do this right now. And it does work, but it doesn't use the suggested construct. Remember, when I assign a question of the day, it's not about just getting it to work. I'm trying to reinforce something we've done in class to get you to use constructs that you might not otherwise use. It's to be familiar with the entirety of the language. My worst nightmare is that I teach this class and everybody comes out writing code that works, but is A, ugly, and therefore not maintainable, B, not documented, and C, uses the tiny fraction of the language that you might be comfortable with, so that every function starts with a for loop. Believe me, people do this. I don't want that for you. It's not. It sort of closes down your perspective, and it will affect your success in later CS classes. I want you to see and embrace the whole language. So this previous solution here, I don't like that solution. This one, I think, is a pretty good solution. It's short, it's to the point, it's concise, it uses constructs we've used in class. Ditto this one. It's an excellent solution. By the way, this is the one I said, I gave you the solution. I said, I don't want the solution. Here I'm just replacing the space in string with no space and then taking the length. It's clean, to the point, nicely done. How about this one? Well, here they split the sentence into words, joined it back together. It's really akin to this one. Take the length, also clean and to the point. The problem with these solutions, they're all excellent. They're all going to get the point. Don't worry, I'll give you the point this week. The problem is they don't meet the specification. When the specification says, use the mapping constructs that we talked about in February 9th, go back and look at the lecture. Figure out what constructs these are. So from here on out, warning, I'll give you the point today. From here on out, solutions that are overly complicated, have unnecessary constructs, don't meet the specification in some way, or fail to use the suggested constructs get 0 points on the questions of the day. This is not just get it done and make it work. This is learn how to use the concepts we're talking about in class. So how did I want it done? Well, this is the solution. If you reviewed this lecture, the first thing in the lecture was a discussion of Lab 2's max element function. And in max element, you remember what we had to do was find the largest element in a list or a sequence. And we did that by using the maximum, and if you recall, this is a structured, like a list of lists or a tuple of tuples or something. What we did is we mapped max over all the lists in S, all the sub-elements in S, And then we got a list back from that, and we got all the max elements back. So this is the magic construct here. Map and max are iterative constructs that don't look like iterative constructs. So this suggests the following solution. You map the length over the split sentence. So what I get back from this is a map of all the lengths of the words. So to be or not to be gives me a list, a map of 2, 2, 2, 3, 2, 2. And then if I use simply sum, which is another one of those mapping constructs that are iterative without being for, while, or a comprehension, you get the solution. This is what I was after. Now, I'll give you credit for the other solutions this time because I wasn't maybe clear about it. But when I give you a hint or say in the spec, use this construct, I'm not just making a suggestion here. I'm telling you, do it to get the credit, okay? Not that the credit matters, right? But you need to try these other things so that you're comfortable with them. You're going to get a lot of questions of the day that say, from now on, we'll say, use the comprehension too. And I know some of you are going to write a for loop, and you're going to get 0 points, and then you're going to complain. But that's the way it is. You need to learn to use all the constructs we cover in class. OK. Bad mood lecture for the day is over. I hope you had a nice weekend. It was spectacular. Got outside, went for a walk. Wasn't 40 degrees below 0. But there's always tomorrow. It will be again. So here we are. All right, where were we? Comprehensions. One of my favorite things. You know, like raindrops and roses, this is one of my favorites. So if you recall last time, we had talked about 3 types of comprehensions. List comprehensions, this is the general form. You have an X variable iterating over that sequence, a Y variable iterating over that sequence, and others if you want. And then you have a condition based on those iterative variables, and you have an expression based on those iterative variables. And the comprehension collects all of these valuations for all combinations of these variables whenever that condition is met. We're going to do some examples today, so you'll see them. Same thing for set comprehensions, except instead of a list, you get a setback. Otherwise, it's exactly the same. And remember, this sequence here and here, any sequence type or collection, even sets can be treated as sequences as the thing you iterate over, except that with sets, you don't know what order you're iterating on. And finally, dictionary comprehensions, which have keys and values that depend on these x's and y's, and there's conditions here as well. I notice I forgot a few dots in here and here, right? Left out a dot there. You get the idea. Depending on how many iterative variables you have, those expressions can rely on all of them. So this is correct, and this one here is not. And we also mentioned there are no string comprehensions. Doesn't exist. Split and join is what you do there. And we also talked about these sort of fake tuple comprehensions, which are really not the same thing. They generate what are called generators, which are evaluated only on demand. What differentiates a generator from these comprehensions is that here, when you evaluate this expression, you get back the whole list. It's constructed for you. With a generator, what you get back is a promise to construct that thing on demand. There's a word for this in programming language design. It's called lazy evaluation, which is a nice metaphor, right? It says, here's a promise to compute this thing, but until you make me do it, I'm not going to go to the trouble, which saves you a lot of time if you don't need to compute it. So we're sort of going to skip these for now, but just remember that there is no tuple comprehension. It's really a generator. All right, let's look at some examples. So max exponent L takes a list, and an integer k, a list of integers, an integer k, and returns a new list that contains each of the elements raised to the kth power. Now, we've used map before. You were supposed to use it in question of day 6. Could you do this in question of the day 6? Could you use map to solve this problem like you did in question of day 6? And the answer is not yet. Map, you may recall from the solution I just showed you, it's okay to map things like max or length or sum over elements of a list or a sequence. That's easy. But here, exponentiation takes 2 operators, the base and the exponent. And if you're mapping it over something, you only have one of those. in the mapping function. So there's no way to provide extra arguments in a simple mapping function. You can map that function of one argument over a list, taking each element of the list as the argument. So the beauty of comprehensions is you can get around that constraint. There's a way for mapping functions too. We'll see that later. But for now, this is the behavior I want. I have a range, 1 to 6, so that's 1, 2, 3, 4, 5. I turn it into a list, and I raise them each to the third power, so 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. Really slick, right? Same thing, raise it to the 0th power, I get back all 1s, because anything raised to the 0th is 1. What about negative numbers? Seems to work as well. So there's my function. It returns the list comprehension. So it's actually going to return this, the value of this thing. The value of any comprehension is new structure of the type it promises. For a list comprehension, we're going to get back a brand new, fresh list, where every element of the list is the form of I raised to the kth power. For every I and L, the k is taken from the parameter list. This function gives me this behavior. It's clean, it's simple, it's elegant. Those of you who've used other languages, you probably are thinking, well, I could do that with a for loop. You could. It'll take you 4 lines of code. It's a one-line thing. It says exactly what it is you're computing. I look at this, and you will eventually look at this and say, oh, give me a list of I raised to the kth power such that I is an L. And by the way, k is whatever I passed in. Exactly like the mathematical notation you use, which is a convenient shorthand. This is the most concise way to express this concept. So it's similar to using map, but in some sense it's a lot more natural, right? It's certainly easier to use, because map is restricted to using mapping functions. It's restricted to mapping functions, things like length, sum, max, min, things with functions of one argument, as opposed to expressions over the sequence. This is an expression we're mapping over the sequence, not just a function name. Now, to do this with mapping functions, you would need to know something about something called lambda functions, which are anonymous functions. We will do lambda functions later this term. But the fact of the matter is, using map with a lambda function, when you look at the way you would have to write it, it's really ugly. It's not obvious, it's obtuse. This is clean, straightforward, and to the point. Collect divisible, max k, takes 2 integers, max and k, and returns a list containing all integers between 0 up to and including max, such that I is evenly divisible by k. All right, so let's see an example. I'm going to go between 1 and 20 inclusive. Notice that this does not fit our normal thinking about range, which includes 0, but doesn't include the high end. And here we're shifted over. We start at 1, but it's close enough, such that I is evenly divisible by k. K is 3, so I get 3, 6, 9, 12, 15, 18. The next one would be 21, but that's out of range, so it stops. If I ask for divisible by 2, I actually get that last element, 20, all the powers of 2. Powers of 5, simple enough, right? Or multiples of 5, not powers. But there's my solution. So I'm going to collect I for I in this range. Now notice the range is a little complicated because I did something squirrely here. If I modulo k is 0. So let's break this down a little bit. The squirreliness with the integer range here is all handled within the range function itself. Right? There's nothing magic in the rest of the expression. This just sets up what the range for this I variable is. Sorry, the domain? Yeah, domain, whatever. What I ranges over. Everything else is handled with this expression. I just collect the I, because these were all in that range. I just collect the I if and only if k into I leaves a 0 remainder. Now to me, this is a very natural expression of collectivision, or collectivisible. But however, in the same spirit of question day 6, In Python, there are many ways to skin the proverbial cat. And you have to be a little bit careful. Okay, what happened? So this filter here is the such that part. I meant to say that, I apologize. But comprehensions sometimes are overkill because this particular very regular construct, this is a very regular idea, is simply the product of the range when I vary by k. Right, so if I look at this range statement, I'm going to vary by 1, and I'm going to throw out a bunch of entries. I'm going to filter them out. But if I'm a little bit more clever about the increment here, I can write in a single range statement exactly what I want this function to do, and then just convert it to a list because I'm told to return a list. Now, to me, the first one seems more natural because it fits in the general class of comprehensions. The second one, however, recognizes that this is a special case. It's a special case that is particularly simple to implement using constructs we already have. So don't get carried away. It's easy to get seduced by comprehensions. Comprehensions are great because they simplify a lot of the iterative structure that you often write that goes 3, 4, 5 lines can often be done in a simple expression. But sometimes even comprehensions are the dinosaurs, and there is an even simpler way to look at it. So in tomorrow's lab, it's not a surprise there's going to be comprehensions. There are also some problems where a much simpler solution suggests itself. And there will be hints about those, so keep that in mind. Let's take another one. Splice uppers takes a string and returns a new string that contains lowercase versions of only the uppercase characters in S. Now notice what's different here. This filter here is not something that can be applied with regularity, right? There may be no uppercase letters. There may be uppercase letters at random intervals. In the previous problem, this filter will be true with great regularity every k elements. It's that regularity that lets me use the special case simpler solution. In this case, there's no promised regularity here at all. There's still multiple ways to solve it. We're going to look at the comprehension way. Here's an example of what it looks like. This finds the I and the T and returns IT. Unfortunately, this suggests that there's a string comprehension at work here that we could use, but remember, we don't have string comprehensions. So the solution I have iterates over elements of a string. So I'm going to iterate on the string S. I'm going to let C be every character. I'm going to collect the lowercase character only if C uppercase is true, which is a Boolean that tells me true if the thing is uppercase. It doesn't convert it. So that sort of works, but I didn't quite get all of it, right? Because I got back a list rather than desired string. But you all know how to solve this. So here is the second way of doing it. The list comprehension stays the same, but it's now wrapped in a join with no space, no character for the glue. And this idiom, this is like a computational idiom in Python to see a join on nothing with a comprehension here and a filter. This is a very common way of emulating a string comprehension. Right? You break it apart. You do what you want to do, throw out what you don't want, and then you splice it back together again. It's exactly what a string comprehension would do. So this delimiter, whatever this delimiter is the glue that joins these list elements together. The glue element here is the null character. So basically, comprehensions are useful even as for strings if you make them the argument of a join. All right. Is there a question? Okay. Count characters S takes a string and returns a dictionary indexed by lowercase elements of S with values corresponding to that element's occurrence count, independent of case. So I give you a string, like my name. And I get back a dictionary where the keys are all the characters of my name, including lowercase versions of the uppercase characters. And the values are how many times that character occurs in that string. So building indices is something that you will do a lot of if you're doing any sort of data manipulation. Doing any sort of text manipulation, you'll build indices of how many times words occur, how many times characters occur, how many times certain phrases occur. And this is often done with dictionary comprehensions. Dictionaries are basically, by definition, indexes of stuff based on arbitrary keys rather than just integers. Otherwise, you might use a list or a tuple instead. So here's to be or not to be. There are 3 T's, 1 N, 2 E's, 2 B's, 4 O's, 5 spaces. This is, after all, a character in S, and 1 R. So my solution looks like this. It is, as you might expect, a dictionary comprehension, hence the squiggly brackets which wrap it. That tells us we're going to return a new dictionary. How is that dictionary computed? Well, it has a key, which is a character. And that C will be the C in the set of lowercase, so I take the string, convert it to lowercase, convert it to a set. That gives me all the unique characters in S. I'm going to let C range over all the unique characters in S. And for every character, I'm going to collect that same S dot lower, this is the lowercase version of S, dot count of C. Now, a couple of things to notice. This method invocation that is dotted can be concatenated. And I think we saw an example of this when we talked about methods the other day. So this kind of C colon S dot lower function dot count argument C is a very common kind of idiomatic expression. So this cleanly solves the construction of this index. This is, you know, I know a lot of you don't have programming experience, but if you have programming experience, think in your head how you would have approached this problem in whatever other language you know. This is a lot more concise than whatever solution you would have otherwise had. It's short, to the point, tells you exactly what you're computing, easy to write. You get used to it, you'll find that you can't live without this kind of comprehension expression. Now, if I wanted to avoid this 5 spaces here, I could simply add a filter to say if C is not that space. Question?
Can you have like multiple conditionals, so if you wanted to avoid spaces and...
So the question is, what if I wanted to avoid spaces and say all the vowels, for example, right? So yes, this is just a Boolean, so I could say if C is not equal to space and C is not equal to A and C is... There's a much easier way. If C not in the string that contains all the characters you want to avoid. So I could say if C not in, single quote, A, E, I, O, U space, single quote. And then I would filter out all those letters. So those filter expressions can be very concise as well. Everything you've learned about logical Boolean expressions pertains to this filter here. Any other questions? Okay, what else? Here's an alternate formulation. It looks exactly the same, except that here, instead of the not equal, I'm using not C double equal. 6 and 1/2 dozen the other. Take your pick. What reads more naturally to you? Doesn't matter to me. Palindrome returns true if the string W, which is a word, meaning no spaces, is a palindrome and false otherwise. So what is a palindrome? It's a word that reads the same left to right as right to left. So this might be like a question of the day. And this is my solution. Yikes. Well, so what's the insight here? The insight is if I have a palindrome, I want to read this way and this way to be the same. So I could say, take this word, if it's equal, double equal to that same word reversed, then I can say that's a palindrome. So the first try might be return W equal equal W square brackets colon colon minus 1. It's fine. However, those who are keeping track at home will recognize that you're doing extra work. You're doing extra work because if the first half of the word is the same as the second half backwards, you don't need to check that twice. In other words, if I compare the word this way with the word this way, I will compare however many letters there are in the word. I'm like that many comparisons. But I really only need to make half of those. Because if the first half reads the same as the last half backwards, then I know that the first half backward will read the same as the last half backwards. Sorry, last half forwards. So here I've just taken advantage of that. What I've done is I've collected I equal minus I minus 1. Again, this is because that counting backwards sometimes is a problem. And I want to make sure the upper range, remember, is off by 1 because I'm going to go up to the length of I. And I'm just going to let I go from the range from 0 up to, but not including, the length of W integer divided by 2. Now, this comprehension here returns the result of this evaluation. What does this thing return? What type of thing does it return? Boolean. This is going to be true or false. And I'm asking to return all of this list, meaning if everything in this list is true, then this returns true, otherwise it returns false. Now in real life, I would not build this way. I would probably do, because words are short, W equals W reversed. Simpler, only does a few more character combinations. Now, if I were comparing strings that are billions of characters long, I would definitely think about doing this. But there are other ways that I would solve this problem better than using this comprehension. But the point here is, comprehensions can be used with a lot of those iterative forms we've already seen, all, any, max, min, sum. And sometimes those things are really convenient. So far we haven't seen for and while loops, but we have seen other forms of iteration. We've seen things like sum and many, sum and any, all, those kinds of iterative constructs. Don't forget that they exist. Use them with comprehensions if this need arises. Again, don't overthink things too much. Here's a simpler way of doing it. Here, I'm not even comparing W to W reversed. I'm comparing the first half of W with the second half of W reversed. This palindrome function does exactly this, but it does it in a more direct slicing construct. So remember, you know map, min, sum, all, any. You know how to use slicing, and now you know how to use comprehensions. You know a lot of iterative forms without resorting to for and while. For and while have their place. We're going to get to those next. And then we're going to talk about when it's appropriate to use a comprehension, when it's appropriate to use a mapping function, and when it's appropriate to use slices, and when it's appropriate to use for and while. They each have their uses. And they signal to the human reader that you're trying to achieve something differently. Okay, are there questions about comprehensions? Are we okay? All right, so that's sort of the end of most of the stuff we want to present, except for iterative constructs, which we're going to do next. So I'm going to talk a little bit about models of execution. This is a step up from what we've been doing. So step back is more abstract. But we all know what a definition of a function name looks like. So we have a function name. This is a signature, bunch of parameters. I can have fancy parameters. I can do a lot of stuff there. But basically, as some of you discovered in the first lecture, unfortunately, you can do a bunch of statements in a row, and then whatever the function returns is going to be governed by whatever return statement you encounter on your way through the function. And we've seen that the default ordering here is to do these things in order. This is why you can write x equals something, y equals something, z equals something else, and so on. That's why it works implicitly. Now, these functions entail executing more than one Python statement. When you type to the REPL, you're saying evaluate this expression. When you construct a function, you're saying evaluate these expressions in the context of the parameters in implicit order that they occur in the function. And that implicit order is the mechanism that governs how to select the next statement to execute. When you do something, what's next is the question the machine asks. So the default answer to that question is, I execute one instruction, I go on to the next instruction in sequence. But there are other answers to that solution as well. So the default mode of execution is something we call sequential execution. That is what Python function statements do. They execute each statement in order, one after the other by default. We could have conditional execution, which you all know of, where I have an if condition that tells me which statement to do next, which may be the statement in the if body, in the else if part if that condition is met, or in the else part if no condition is met. So I can alter sequential execution by inserting conditionals that make some statements optional or some statements alternative paths through the function. Iterative execution is either bounded or unbounded. So let's talk about this for a second. We've talked mostly about what is essentially bounded execution. When you map a sum function over a list of lists, that list of lists has a fixed number of elements. It's not changing. It's not dynamically growing and shrinking. There were 13 elements you wanted to add together. It's going to add those 13. Doing the addition is not going to add a 14th element or remove some elements along the way. The list is statically fixed. The elements are known. You perform the map and you get an answer. That's an example of bounded iteration. Unbounded iteration is different. That list might be changing dynamically. You might not know before you start iterating down that list how many times you'll have to iterate. That can come if the list is growing and shrinking, like it might be doing in a discrete event simulation, or if your iteration is such, the most common type of iteration that doesn't execute that many times is one that looks for a value. Find 13 in this list and tell me where it is. We've seen a method for this, the index method, that says s.index some expression will return where the first occurrence of that expression will be found in the list. But notice, it doesn't have to look through the whole list. If it finds a match in the third spot, we're done. It just returns 3. If it finds no match, it will only know that if it goes through the whole list. So that iteration is kind of different than the one that says add the numbers in the list together, because you never stop early. So to review, bounded iteration is iteration that executes over every element of that iterative scope for sure. It will always execute over all elements. Unbounded iteration is one where the list might be fluctuating in size over the course of the iteration, or you may not need to go all the way through, and you can get an answer early and exit. So iteration comes in these two forms, and we're going to talk about which iterative construct is appropriate for each of these forms. Another execution model is the function call. We have written functions that are mostly standalone. You write a function, you use it, and it returns a value. But in this part of the class, starting about now, we're actually going to write functions that work together. So you might write a function that does something, and then you might write a function that does something else and uses that previous function as a subroutine or as an element of its solution. We've seen one example of this already when I had the circular left statement. We wrote a circular left function, and then I asked you to write a circular right function, and all you have to do is reverse the sign and call circular left. Remember this? It was like 3 lectures ago. So this is a very common kind of execution, change in execution. And the way to think about it is I'm executing my function, I'm stepping forward sequentially, I get to a function call, I stop executing in this function, I go over here, call the other function, execute that function. When I'm done with that, whatever it returns, I come back here and insert it as the value of that function call, and then I proceed. So there's sort of stop, go do the other thing, and then come back. That's kind of the function call invocation idea. Finally, which we won't do much in this class if at all, parallel execution. These may be real parallel statements. It is possible to write codes that runs on many, many machines at once, or on several cores at once. Or these may be actually running on a single machine in a single CPU, but they may be conceptually parallel, so that the operating system can manage them independently. Now, this is not stuff we do a lot in CS1, if at all. But these are ideas that you will see as you proceed through the CS curriculum. It's kind of the exciting part of CS, right? This idea of, can I split the work amongst everybody in the class and then just collect the results and do the work that many times faster? And the answer is only sometimes. Sometimes you split the work among many people, the cost of doing it actually goes up. There's so much coordination cost that the overall cost of solving the problem is more than if you just did it on one machine. These concepts are more advanced. We won't talk about them in this class, but it's good to sort of know they're lurking back there. Okay, so conditional execution, we've seen this before. You've read about it in your book. If condition 0 is met, I'm going to do these statements. Otherwise, if this condition 1 is met, I'm going to do these statements. Otherwise, there's an optional catch-all where I do these statements. Fairly clear. Notice how the bodies of each condition resorts itself to the default sequential execution. In other words, within the body of that condition, I have sequential execution, which is the default mode of execution. So this is a fairly simple example. It's an if with 4 clauses. If I write test 613, I check first this very first condition, which is actually met because 6 times 2 is less than or equal to 13. So I actually execute this statement, which gives me this printed statement, and then everything else here is skipped. 1113, well, A isn't so small, so this condition fails, but this condition triggers, so I execute this. Notice that each condition in an if-elif, or else-if, is evaluated in turn, and the first one that matches is the body that's executed. Only if none of them match do we do the else. So if I test 100 versus 13, this condition is not true, this condition is not true, this condition is not true, so I print this. Sorry, I got a slide malfunction here. At most, one subset of statements will be executed. If you take that else clause out, if you take this else clause out here, you may not get any output from this function if it doesn't meet one of the other else-ifs. All right. You can sense the excitement in the room. I'm talking about while, and then we're going to talk about for. The iterative form, the basic iterative form in Python, comes in 2 shapes and sizes. The first one is the while. The while looks like a lot like if, in the sense that there's a condition which must return a Boolean, just like the if conditions must return Booleans. And if this condition is true, I'm going to execute all these statements. Then I'm going to come back, I'm going to evaluate the condition again. If it's true, I'm going to evaluate the statements again. And I'm going to keep doing that until this condition evaluates to false. So the first gotcha here is, notice how comprehensions are intrinsically bounded iteration. You don't have to worry about them running forever. Why? Because there's a fixed number of elements in the sequence you're iterating over. Here, if you're not careful about updating what this condition is so that there's an out, this code could run forever. You can write an endless loop and your code will never terminate. So ensure that this Boolean value, the return by condition, will eventually change to false. So there better be some statements in here that alter or mutate the elements of that condition. Because if there aren't, you're in trouble. Another form of this, for, well, the for loop is actually perfect for bounded iteration. You may have, if you think about it for a second, this particular loop is really good for unbounded iteration. Why? Because it doesn't really know a priori how many iterations it's going to perform. It all depends on when this condition stops being true. Could be 1, could be 100, could be 1,000,000. You don't know. So this loop is particularly good for unbounded iterative execution. The corresponding form for bounded iterative execution that corresponds to for is the for loop. But the key thing here is choose when you use for, when you use comprehensions, and when you use while. They're not all the same when you use map, etc. So here's the example of 4. I have 4 variable in sequence, bunch of statements. This variable, it's called the iterative variable, will take on successive values, successive elements in the sequence as its value. In this sense, this 4 variable in sequence looks a lot like the introductory part of a comprehension. Collect this for I in list. And inside the for loop, this iterative variable will have the corresponding value of the current iteration. So I can use I inside the scope of the for loop, just like with the comprehension. Same idea. Same notion of an iterative variable that is meaningful only within the scope of the comprehension. There's an iterative variable that's meaningful only within the scope of the for loop. If I evaluate this, range 3 is 0, 1, and 2, so I will go through the loop and successively print I, so I get 0, 1, 2. At the end of the loop, when this is exhausted, the for loop will terminate. And I know, I can tell you right ahead of time, before I even evaluate this, this thing's going to go through that loop 3 times. Because I know the length of range 3 is 3. Compare with the while, I have no way of knowing when the condition will change. There's a definite difference. So here's an example. Notice, for those of you with prior language experience, one of the ugly aspects of learning a different language first is that when you get to Python and you're so happy to use your for statement, you would write this as for I in range length hey, and then you would say print C square bracket I dot upper. Why? Because in most languages, the iteration is an integer. The iterative variable is an integer by default. It's not an arbitrary thing. Here in Python, the iterative variable takes on successive elements of any sequence type. So the iterative variable here directly has the character values. It's much simpler than having to use an index to index that sequence every time through. So don't fall into that trap. Just one more minute, we're almost done. So here's an example. For W in, this is a test split, I'm going to add that extra character, and I'm going to update S every time through. And that gives me, this is a test A is this, which is sort of what I wanted, because I'm adding it to the end. So we'll do this example when we're not running, it's 20 after. The point is I'm reconstructing the string back to front here, so you can see a little bit of the flexibility. I can as easily do this with the comprehension. All right, I'll see you on Wednesday. We'll go over the exam and take it from there. Remember,